Yeah, camps on everyone. Hope everyone has tried the 3 homework problems. I hope you guys didn't forget about it. Great. Anyone got the answer for this thing? I gave you the answer for time period. How do you get the amplitude? Anyone got it? If you got it, you can just say yes or thumbs up or something. Or you guys forgot to solve the question. Amplitude 12a by 35. I don't remember the answer. 35 aaya kya? That was unexpected. I think that is wrong, Samyak. 1235. Okay, other scams on. Let's start off. So how do we do this? So like I said, these are the 3 pretty good ones. You should have spent some time. You could have spent even an hour on these 3 questions and it was worth it. Okay, let's see. So the problem here is what? One is a hollow sphere, one is a solid sphere, and you pull them apart by A. So let the elongation in the spring be X. So the issue is both will have different frictions. Both will have different accelerations. So we have no idea how it goes. So let's see. So this is a hollow, this is a solid. So let's say this thing move by distance x1 and let this thing move by distance x2. And because of x2, this will have an acceleration a2 and this will have an acceleration a1. Now, if you look at the forces, this will have a spring force, which is k into x. Now, again, remember, x is nothing but x1 plus x2. So if you assume the left one is going x1 and the right one is going x2, then your elongation will be x1 plus x2. And this will be some friction F1. This will be your Kx, and this will be your friction F2. This is the first thing, the free body diagram. I'm not writing the vertical forces. This will also give alpha 2, and this will also give alpha 1. I hope everyone got the FBT part here. Now, when we take torque, we take our favorite point here, A, and we will take our favorite point here, B, the bottommost point. So when you take torque about A, the friction F1 ka torque will go off. Kx ka torque will be minus Kxr, right? And this will be equal to I about A alpha 1. So this will be minus Kxr. Ia will be hollow shell 2 by 3 plus this thing. So 5 by 3 mr square alpha 1. So that would be A1 is equal to minus 3 Kx by 5 mr. Now be careful. This is not what you want. What did you displace? You displaced it by x1, isn't it? So if you displace it by x1, then acceleration a1 must be equal to minus omega square x1. Are you getting it? The acceleration must be proportional to the displacement of the body. When you displace that sphere by x1, then a1 must be proportional to x1. But you got here a1 proportional to x. This is not your omega square. Similarly, a2 will be minus omega square x2. I hope you're getting the problem there. What you got here is a1 and a2 in terms of x, but what you want is a1 and a2 in terms of x1 and x2. So same way, if I take torque about B, we can do the same stuff here. Minus kx into r is equal to, won't finish about B into alpha 2. This would be minus kxr, and IB will be 2 by 5 plus mr square, 7 by 5 mr square alpha 2. This would give you A2 is equal to minus 5 kx by 7 mr. Again, the same problem. We don't want this. This is your equation 2. Now, what do we do from here? How do we get x1 and x2 here? Now, if you notice something here, if you divide a1 by a2, right? So kx by mr will cancel off. You get 3 by 5 by 5 by 7. You end up with 21 by 25. This is the ratio of the acceleration. But this is also equal to, we know a1 and a2 is minus omega square and this, right? So this is minus omega square x1 and minus omega square x2. Indirectly, you got a ratio. Let me show you on the next page. But any doubts on this page so far? All clear with this? So when you do a1 by a2, which is minus omega square x1 minus omega square x2. See, the omega will be same for both the things. Why? Because they belong to the same system. They have to have the same time period. If they don't have the time period, the motion won't repeat. So then this guy is minus 3 by 5 and minus 5 by 7. So we get x1 by x2 is equal to 21 by 25. Perfect. This is the ratio of the displacements, right? And we also know x is equal to x1 plus x2. So if you substitute here, we get x is equal to x1 plus x2 will be 25 x1 by 21. So we get x1 is equal to 21 x by 46 x1 by 21. Yeah, perfect. Take this and put it in equation 1. So we know we got a1 is equal to minus omega square x. So take this and substitute in this. Why do I get a feeling I messed up something here? 21 by 25. x2 is 25 x1 by 25. Wait, a1 is what? Minus 3kx by 5mr. Now substitute that x there. So this will be minus 3k by 5mr. R won't be there. I wrote a is equal to r alpha, no? That r goes off. That was a mistake. 46 x1 by 21. So we get a1 is equal to minus 46 by 35k by mx1. There. That is your omega square. You can do the same thing with x2 also. You will get the same answer. You will get the same time period. That's your omega square and you're done. Therefore, the time period will be 2 pi root over 35m by 46k. And for amplitude, we also know A1 plus A2 must be equal to the total amplitude A. And they will be in that same ratio there. So A1 will be 21 by 21 plus 25 into A. 21A by 46. A2 will be 25A by 46. Clear with this? So the first thing is the free body diagram. Let the spheres go x1 and x2. Let the accelerations be a1, a2. Then you draw your FBD, then you solve. And this thing, right, is not the first one. We did this thing, isn't it? Something similar there. We used to take the torque about the bottom because it's not slipping. The problem you face is you will get a1 in terms of x and a2 in terms of x. So you need to realize what you want was actually a1 in terms of x1 and a2 in terms of x2. That is the thing you need to realize. And then you will need to think like, okay, now how do I get a relation between x1 and x2? So when we divide these two equations, you will get accelerations will be in the ratio of 21 by 25. And since a is equal to omega square x, so x also must be in the same ratio. And then you're done once you figured it out. All clear with this? It's a really good one. You should definitely try this on your own again if you have not got it. But I hope everyone at least figured out till this part, the FBD part. You should have got till there at least. So I can change the shapes, right? I can keep a hollow cylinder, solid cylinder. You can keep a sphere and a cylinder. You can play around now. It works. Any doubts on this? Clear? This would be a good more than one choice question. This one is a really good one. How do we do this? Any chance anyone got this? This is a little complex. So multiple things are happening here. Let's see. So this picture, let me redraw it again. This is the reason I gave you time. Like, I wanted you to spend some time thinking about these three questions. See, so this was the sphere here. Initially, it was like this. You got a spring here. You got a spring here. Okay. Now, whenever you want to find time period, what you do? Displace it by small theta. So we will rotate this sphere by small theta. Now, let's see what is happening at different places, okay? This position here will go down by r theta. Because you're rotating, this point will go down by r theta. See, again, I'm not touching the rod, okay? Let's do one at a time. Forget about the rod. Let the rod be still like this only. We'll do one at a time. If you rotate here, this point will go down by r theta. This point will go up by r theta. Agreed? Means just because you rotated the spring, rotated the disk, the spring will compress by r theta and that spring will compress by r theta. Clear? Now, but when you rotate this rod is not going to keep quiet. This rod also will start moving here. So this rod will become something like this. So this was point P and this was point Q. Now, technically speaking, the rod should not be able to rotate because P and Q are fixed. But for small rotations, right, we can assume this thing has moved a bit. Something like this. I'm exaggerating the figure. It doesn't move this much. It can't move this much. Something like this. Do you agree? This thing will twist. By what angle will this twist? This also will rotate by theta. So if the disk rotates by theta, this thing also will rotate by theta. Agreed? Now, because this guy is rotating, now see what happens. This thing which is connected here, so this point is being actually, what is happening? Initially, it used to be somewhere here. It got compressed by this amount. How much is this? What was the length here? This was 3r. So this length was 3r. Again, this is small theta. So this thing pushes it up by 3r theta. So did you see what happened here? This 3r theta is the compression because the rod rotated. This r theta is the compression because the disk rotated. So that means this spring in total, it got compressed by 4r theta. Any doubt still here? Got it? Great. Now, if you draw the FBD of the disk, now remember, why is this spring not affected? Because if you see, right, the spring and this thing, right, are connected separately. The spring is not connected to the rod. The spring is connected to the disk. So this guy moving here is not going to affect the spring. I hope you got the difference. That spring was actually connected to the disk. Now, if you draw the FBD of this disk, let's see what are the forces. We have this spring here, which is pushing down with K into R theta. We also have that rod. That rod is also pulling it down. So let's call it Ty. This is the Ty is the tension due to the rod in the vertical direction. The tension will be actually at an angle, but uska vertical component hai. This is the rod vertical component of rod tension. And here, this spring here is pushing it up by k into 4r theta. I think the spring constants are different, na? K1 and K2. So this is K2 and this is K1. All clear so far? So I know K1, I know K2. So if I'll take torque about the center, now my only headache is if I can find Ty, my job is done, isn't it? I still need to find Ty, the tension in the rod. This is where you get an interesting thing here. So look at what is given here. AB, AC, CD are massless rods. So the word is important, massless rods. So massless rods have this property. Let's see how the picture look like. So when I rotate this rod, this guy has become like this. Again, I'm exaggerating these figures. So if you look at the tension in the rod here, again, this is the thing is very small actually. So the rod will be just pulling it up. I exaggerated the figure too much. So it's like this is your Ty and this is your like Tx, right? This is your P and this is your Q. And here the spring force is also pushing it. So that would be perpendicular again here, K2 4r theta. Again, remember, the figure, right? I should have maybe drawn it more little close. Let me do that only. I'll keep it like this only. This would be Ty and that would be some Tx. And the spring force here will be K2 4r theta. This is better anyway. This is P and this is Q. Yeah, net force 0. Now for rod, if you take torque about the PQ line, we have Ty, and what was this distance? This distance was R. This distance was 3R. So that will be Ty into R minus K cap. This would be K2 into 4R theta plus K cap. Right? This will be the torque. But we know torque is equal to I rod into alpha. So this would be Ty minus Ty_r plus K2 4R theta. And what is the moment of inertia of the rod? This is 0. Why? Rod is massless. Therefore, from here we will get Ty is equal to 4 K2R theta. This is the tension of the rod. So whenever you have a massless rod, the net force is 0, net torque is 0. Wait, I did one more mistake. K2 4R theta into distance is 3R. That would be 12. Please have a look at this. This is your tension Ty. Got this? Now we will take this and substitute here. So now when you take this system here, torque about the center, K2 4R theta into R, K1 R theta into R plus Ty into R is equal to I disk alpha. This would be minus mr squared by 2 alpha K2 4R square theta K1 R square theta plus Ty is 12. K2 R square theta. R square goes off, you end up with alpha is equal to minus 2 by m 16 K2 plus K1 theta. This is your omega square, everyone. If you send 2 inside, you get 32 plus 2K1. And that is your 32 plus 2K1. This is a really tough one, meaning if you have not seen something like this before, exam, if it comes for the first time, it doesn't click. And that is the whole point. That is the reason I keep telling you, whatever you solve, you should definitely resolve them again. That is when the problem becomes yours. I'm not saying they'll ask the same question. They can ask something, a more simpler version of this. Then you can always relate, okay, I have done something like this, so I have an idea there. This thing, right, I noticed a lot when students, right, even though the question is completely new, but if they have seen something similar, maybe 20-30% similar, right, you don't actually panic in the exam. People are very calm and very steady and they do it well. But if it is something completely new, right, then you start worrying and tension and all. So it helps. Why all that currently your senior revision is going on? So right now what they're doing is the entire class notes, we have almost 1300 to 1400 questions. They're just doing the notes only properly, thoroughly. There's no point in doing n different things. So, right? So make sure to do it again. I'm sure you must have got one or two ideas here, but one or two things must have been completely new. Like, that the torque about the rod, if you take, this will give you the tension. Or maybe you didn't figure out about Ty. Could be anything. Or maybe you didn't figure out this will get compressed because of two different things. And that's okay, right? That is how you learn. So that's what I was saying. No matter how many books you read, you will not learn these kind of things until unless you solve a problem. All clear with this? So please make sure to do this again. It's a pretty good one. What about this one? I think out of the three, this is the easiest one. How do we do this? Same story. Choose your system, displace it by small theta. So we will take this guy and we'll displace it by small theta. So here the spring will stretch by L by 2 theta. This point here, so if this rod goes with alpha and this thing stretches by theta, so this point will have an acceleration A is equal to L alpha. And remember, this point is connected to the block. That means acceleration of the block also must be L alpha because they both are connected by the string. So that is one relation there. Now let's draw the FBD there. Remember, we are writing FBD of change in torques. So we are writing change in torques here. So let's see what all torques changed. So when you pull the block by theta, did the spring force change? Yes. So will the spring ka torque change? Yes. So the spring ka torque will be K into L theta. When you rotate, initially what was mg ka torque? 0. But now is there an mg ka torque? Yes. That's the reason you'll put mg. Mg ka torque is there. And this will be T. And this would be alpha. So when you write the torque about the hinge, remember all these are change in torques. The spring force will be KL theta into the perpendicular distance L by 2 cos theta minus K cap. Mg ka torque is Mg L by 2 sin theta plus K cap. So even though Mg is not changing, Mg ka torque is changing. So we have to include it. The tension ka torque will be plus T into L cos theta. That is also K cap. This is equal to I about the hinge, which is ML square by 3 alpha K cap. Directions are important. So what I don't know here, I don't know the tension there. So how do we get the tension? Draw the FBD of the block. So all these are change in torques. This will be tension and this will be acceleration. So for the block, this will be T is equal to minus MA. Again, this is your change in tension. Here we don't write mg because here when you're writing forces, there's no change in force there. Perfect. You got everything. Substitute here. How much is this? K minus K L square. Again, remember for small angles, sine theta is approximately theta and cos theta is approximately 1. Right? And torque due to mg changes. So that's the reason we are including mg for torque, but not for forces. So this guy would be minus K L square theta by 2 plus mg L by 2 theta. And tension is minus MA. So this is minus MA is equal to ML square. And yeah, A is equal to L alpha by 3. A is equal to L alpha. So you can substitute that there. We get a minus theta KL square by 2 plus GL by 2. That would be 4 by 3 ML square alpha. So we get alpha is equal to minus theta 3 by 4 M L square you can divide. That would be K by 2 plus mg by, if the minus sign will come here. There, that's your omega square. Did I miss something? Yeah, I messed up this guy. Wait, this is L by 2 theta. This is L by 2. This was 4. This was 4. Now it looks better. Clear this? That's your omega square. So we get time period is equal to 2 pi. Yeah, you can substitute that. Four m by 3 k by 4 minus mg by 2l. So now they can ask you an important question like this. Under what condition will this make an SHM? Think about this. In the denominator, you got a negative sign. Yeah, right, obvious. Spring force rotator. So if this quantity, right, if k by 4 minus mg by 2l becomes negative, the time becomes imaginary. That means t is undefined. That means this thing is not going to oscillate. This is an unstable equilibrium, basically. Just imagine a situation where this rod ka weight is very, very heavy, okay? The rod is so heavy, the moment you displace the small theta, the mg ka torque is dominating so much, the rod will just keep falling forever. You're getting it? The spring is so weak, it couldn't pull the rod again to the vertical position. There's a possibility like that, right? And that is the reason you're getting a minus n in the answer. Now, maybe we didn't think about it, but Max is saying, boss, there is a possibility. If your KL by 4 is less than mgl by 2, the spring will be so weak, it cannot pull the rod up again. So the rod will just keep falling down forever. So this will not oscillate. So the time period becomes undefined or doesn't make sense. All clear with this? So that's what makes this question good. It is easy to solve, but they can frame the second part there. Find the value of K so that this thing oscillates in SHM. And then you get some values there. All clear? So these are the 3 good ones. So let's see a few more mains level questions and then we'll go again a little higher. So let's say we got a ring here of mass 2m. We have a ball here of mass m. L is the length of the string. So this is a ring of mass 2m. It can move only left and right on a smooth rod. Find the time period for small oscillations. This will be a good mains level question. See, that's what I keep telling you. Your standard mains level questions, you should be very thorough with it, because these are the kind of questions you'll get them in mains and bits. Advance is one part, but mains is also a priority. Your seniors ka mains exam has started today, the second shift. Get this. Let's see how you handle this. What is the catch? Think of like this. Since the oscillations are very small, is there any horizontal force on the system? No. So center of mass is not moving horizontally. So since the oscillations are small, we can neglect the vertical up and down motion of the SHM, and we can treat the center of mass as a fixed point. So you can just make an argument, this point behaves like the fixed point. So this thing acts like a pendulum of length 2L/3. And you can say 2 pi root of 2L/3, which done. That's it. You'll get the answer in one step if you do that. Clear with that? Now, you want to solve normally, then we will say, okay, it got displaced by a small theta here. And then we'll say this is the tension. Then we will write, the tension, this component here, this will have a tangential. And then we have to do tension. We can do that. Again, we'll do all that approximations. We'll still end up with the same answer. But, this is the fastest way to do this. Assume it is almost fixed at the center of mass and finish it off. The center of mass does not move horizontally. It does move up and down a bit. But since the oscillations are very small, you can neglect that. That is the whole point of small oscillations. Since the horizontal forces are zero, right? It moves up and down. It does move. It's not like it is at rest. Yeah, then you're done. So this is your COM. This would be 2L/3. And then you will say tension is equal to 2 pi 2L/3G. Make sense? So we can assume like a simple pendulum with COM as a fixed point. Yeah, that's an easy one. Next one. Let's say we have this elevator. Inside we have a mass m, length L. Gravity is present, and this guy is going up with A. Gravity is there. Find the time period for small oscillations. What if the elevator is going horizontally and you have a pendulum inside? Mass and length L. Again, find the time period for small oscillations. Let's say we have a pendulum here whose mass is rho b. This is dipped inside a liquid. Rho body is greater than rho L. Again, length of the string is L. Find time period for small oscillations. The first one is a proper CT level equation. B and C can be mains orbits level equations. Get them. Easy stuff. Right, Samyak. You guys know where we did this thing? In NLM. Yeah, then G effective. There is a concept of effective gravity. In case you forgot, we have done this in NLM. In pseudo force, I taught you this. Effective gravity. So box is going up, you can assume as if the gravity is G plus N, you can finish it off. If the box is going horizontally, the person will think G effective is this. We have done this in fluid mechanics also. So I'll put it here. You can refer this later in case you forgot. Get the C part. C is a really good one. Try. I'll give you a minute, then I'll show you all three. Hmm. Rho G on minus. Okay. That looks right, Arya. Get the third part also. So you got the A and B part right. Third part. All are stuck with the third part. So how do we do this? So here, what will be the G effective? G effective will be G plus A. How do I know that? So in case you don't know how to do that, look at the forces mg. Because it is going up, the pseudo force also will be downward ma. Right? So the system here will think the tension T is m into A plus G. So that is nothing but m into G effective. That was the idea there. The string does not know who is gravity. So string will start thinking, okay, this guy is placed in a planet where the gravity is G plus A. The same story here. Here, when you apply the pseudo force ma, and there will be an mg down. We have done this in fluid mechanics also. The both are perpendicular here. So G effective will be root over A square plus G square. Here we have tension. We have mg, which is rho B Vg. This is your bind force, which is a rho liquid Vg. So here the tension will be rho B minus rho L Vg. And you want to write this thing as m into G effective. So putting in the liquid, right, the ball will start thinking the gravity got changed. So this is rho B minus rho L. Mass of the body is rho B into G. That's your G effective. That's it. Once you got this, then the time period 2 by root over L by G effective. Take them, dump them, you'll get the answers. All clear with the idea there? Right, Utsa. I know, Arya. I saw all three parts. You got it. Right, Samyak. Right, Anvita. Others, clear this. Easy one, right? Not tough one, but see, these are the kind of questions in it won't take more than 2 minutes to solve. So then, next one. This is another good one. So we have a rod here. We got a hinge here. We got a mass M here. And you tied a rope here. This is height H. This is a string. This is length L. And this is length L. This is a massless rod. You getting how is the picture? So we got a massless rod of length 12. Someone attached a string at the midpoint. Now, when you disturb this thing starts oscillating in and out. Right? So this is a massless rod. Hinged at one end. The other end is attached to a mass. And a string is tied to the ceiling from the center of the rod. So, how does this thing oscillate? How do I show you this? So let's see if I can show you this. Look into my screen. So if this black thing is there, if this is your rod, this is what you're doing, okay? You're hinging it here on the corner. So try to look at this thing. I'm hinging it here. Okay? You kept the mass here in this corner. And you have a string from here, right? I need a string kind of thing. I don't have it. I do have something here. So this cable is there. This is like a string here. Now are you able to visualize? So look at this thing again. This is the rod. I'm hinging on the left hand side. So my hand here is the hinge. On the right side, there is a mass here. You have a string here like this. So this string is supporting the rod. Now, if I displace this, see how it rotates. Meaning, if you see the front view, right, see, it goes like this. Meaning, I'm exaggerating the figure, but देख रहे कैसे जा रहा है? This is not going like this, it is coming out, okay? It is going up and it is going like this. Are you guys able to visualize that, how it is going? So this thing, right, when it oscillates, it is actually going like this. It's going in and out of the plane. So it looks like this, okay? The path, right? See, it is not like this. It's not a U shape like this. It is U shape, but like this. Are you guys able to visualize that? Why it can't be like this? Think about this. Because the length of the rod is constant. See, if this is the mass M, the front view, right? It can't go left and right like this because the rod has to stretch. So every time it tries to go to the left, this will actually go like this up. You're getting how it goes? So what you get is a shape like this. You get a shape, U shape, bent like this, inwards. Are you guys getting with that? Everyone able to visualize how will the motion happen? So how do you find the time period for this thing? So here the ball goes in and out of the plane. Again, this is a kind of a problem where like you should have an idea again. So take a minute and see. Let's see if you can figure out something. Applying forces and torques is very difficult on this because going in 3D, you can't even visualize how will the tensions and the forces act. But when you look at the path, right, it just looks like a pendulum actually. So you have to compare this to a simple pendulum. Listen, I'll show you one. I'll ask you one more like this. So in these kind of questions, right, the idea is we are going to use IIR. Remember what is IIR? Instantaneous axis of rotation. How do you find IIR? You need to find at least 2 points whose velocity you know, or you need to find 2 points whose velocity is 0. Can you find 2 points here whose velocity is 0? One is the hinge, which is not moving. One is the top point of the string, which is not moving. Agreed? So this is how you do these kind of problems. Find 2 points on the system which are at rest and join them. You can do this always whenever it is connected to multiple points. Normally, if you see simple pendulum or a physical pendulum, they're always connected to only one fixed point, isn't it? But if you see here, it is connected to 2 points here. Right? And join them. This line is your instantaneous axis of rotation. This is your IAR basically. So when you join these 2 points here, so you can say now this guy is rotating about this line here. Now from here, if you drop a perpendicular 90 degrees, this is point C. Now just look at from the perspective of the pendulum. What will it think? Now it doesn't care about rod, gate, everything. It will think, okay, there is a wall here. This point was A, this point was B, and this point was C. And someone connected me here with a string. Right, I'll call this point D. So someone connected the string here. Let's call it CD. And there is a mass M here. Right, and this will be some gravity constant. So there will be some G effective. You're done. So then this will say simply, okay, the time period must be 2 pi root over length from C to D by the G along CD. Now, can you find the length CD? We can find the length CD. Can you find the gravity along CD? We can do that also, and then you're done. So that was the idea there. So we need to find length CD there. Let this angle be. So this is the gravity. So you need to find in this direction. Let this angle be alpha. So this direction, the component will be G cos alpha. So the pendulum will think the system is behaving as if the gravity has become G cos alpha. If that is alpha 90, then this will be 90 minus alpha, and this will be alpha. So tan alpha will be h by L, and sine alpha is the opposite side. If you take the big triangle, sine alpha, here I'm taking the triangle ACD. Sine alpha will be opposite side CD by hypotenuse 12. You got everything. Dump it here. 2 pi root over length will be CD, which is 2L sine alpha. C along this will be G cos alpha, and that will be tan alpha. But tan alpha is h by L, so 2h by G. Got the idea there. I could have taken this as L1 and L2, then it will depend on the length of the rod. Luckily here, because the both are equal, it got cancelled. But if you take L1, L2, you will get the answer in terms of H, L1 and L2. So don't think it became independent of the rod. Luckily it happened here. So what is the trick in this kind of questions? So think about it. Till now, all the problems you did, right? There was only one fixed point. Meaning here, so there's no fixed point only, right? Especially when you take the simple pendulums. So there was one hinge, right? This was a fixed point. There is one fixed point. There was one fixed point, right? For this pendulum, there is still one fixed point. So how do you know when to use this? You can clearly see that it's connected to 2 points. That is when you should get an idea. Okay, if I join these two, this will become an IIR. All clear with this? So same thing on this. So I will just keep it in the same sequence, 43B. We will not solve the whole thing. You just tell me what will be the steps and then we can go ahead. You can solve it later on. So we have two walls. So we have mass M here. This is L2. This is a string. This is L1, that is also a string. So this is A and this is B. So basically you're connecting a particle to two strings, but this is 90 degrees. Gravity is there. The distance between them, this is A. And the difference in height here, this is B. Find the time period for small oscillations. Yeah, the answer is a little bad. You have to do a little math, but did you guys figure out how to start? Step one, choose 2 points which are not moving or fixed. What are those 2 points? A and B. So that's your IIR. Then step two, drop a perpendicular from this point onto the string. So let's call this C and let's call this thing D. So you need to find, so if this was gravity, if you take this as alpha, then your G effective will be G cos alpha. And then the time period will be 2 pi root over the length CD by G cos alpha. I leave it to you how to find CD. That's little work. You have little math you have to use. You already know this side, isn't it? So this thing will be root over a square plus b square because this is 90. This is a square plus b square. If I take this angle as theta, I can use cosine rule. I can find theta. अगर वो theta आ गया, then yeah. So this is 90 there. I can find this angle also, but I can actually find this angle as theta. Then this angle will be 90 minus theta, right? But be careful with the picture here. This guy is going straight. Yeah, so it goes a little messed up. So try and solve it. I will leave it to you. You guys are pros in this math. Someone got something. Arya got something. Okay, that approximation. You could have done that also. But why yeah, visualization in 3D is a pain. Clear with this? Got the idea how to do, right? So you need to get that lens CD and get angle alpha and finish it off. So then it becomes more of a math problem. Next one. So this is how you handle if you're connected to more than 2 points, 1 point. Yeah, IR will make your life easy, na? और कुछ नहीं था मतलब. Let's say we have a pulley here. We have a spring. We have a block M. Okay. This is a pulley with mass. So this is a disc, mass M, radius R, and there is no slipping. So in this case, the disc also will start rotating. Find the time period. See, before when the pulley was smooth, na, you know what was happening? Look at the picture. Look into my screen. This is how it would look. So if this was the pulley, right, the bottle here, that string, which was, if this was the string, you know, if it was smooth, this was what was happening. The block is going up and down. The pulley never rotated. But now, you know what is going to happen? The pulley also will rotate. I hope you're getting the difference. We did a problem like this when the pulley was smooth. So when the pulley was smooth, the pulley will be there. The rope is simply going down, coming up, going down, coming up. Only the rope was moving. But now if there is a friction between them, even this will rotate. So we have done this kind of things in rotation. If you remember, the pulley has friction. The tension will be different on both the sides. Find the time period for small oscillations. Do you guys remember how we did this kind of problems in rotation? Net torque method, yaad hai? We take the mass. Tell me one thing. Will this length of the string affect the problem? No, right? So then can't we just take it and attach it to the mass? That would be the easiest one to do. Or else you can just take them separately and solve. But this would be the fastest way to do. So we'll just take the mass and attach it here, M. Right? So attach the block at the point where the string meets the pulley. This now, where we did, you know, we did this in rotation. These problems. Net torque method. Do you guys remember this? We just as you attach them and it used to become pretty easy there. Page 142, rotation mechanics. Yeah, then you're done. So if I displace this by theta, the spring here will go by r theta. So now if you look at the forces acting on this system, again, mg ka torque will not change. It's too small. This will be k into r theta. So we get torque is equal to k into r theta is equal to minus I of the system into alpha. Now, what is I of the system? We have a disk and a particle. Disk is mr square by 2. Particle is mr square. This is for the disk and this is for the block. Alpha is equal to minus 2k by 3m theta. Clear with this? You want to do it normally, you can do it. Then you will write here, this is the tension, this is the acceleration, this is tension, this will be k into r theta, this is alpha. Write one torque equation, one force equation, eliminate the tension, you will get the same stuff. So the logic of this method, right, is this. If I decrease or increase the length of the string here, will it change the answer? No. So let's make it 0 and attach it to the block. So that still shouldn't change your answer. So it works. Clear with this? Take a break. Come back by 9:40. We'll continue from here. Any doubt so far? Great. So we got a circular bowl here. So in this small solid sphere, mass m, small radius r. You displaced it by angle theta, and this whole thing ka radius is r. Theta is small, and this sphere is not slipping. So the sphere is rolling in a circular arc. Find time period for small theta. Sure, camps on everyone. Let's go ahead with this. So this ball here is rolling like this, comes here, and then rolls back again, comes here, and so this is oscillating inside. It's rolling in and out. How would we handle this? So here you have to be careful. Huh? There are two different angular accelerations here. So when you displace this by theta here, right? So we get alpha here. So be careful. We want this alpha in terms of theta, isn't it? When you displace that ball by theta, this angular acceleration of this line must be proportional to minus omega square theta. Fair enough. Now this ball which is there, when it is moving, it will have friction. It will have normal reaction. This will have mg sine theta. This will have mg cos theta. And all that stuff will be there. And it will have an acceleration A, and it will also have an angular acceleration. Let's call it alpha dash. So be careful. The common mistake is people find this alpha dash in terms of theta and they think they got the answer. So that's the thing you have to be careful. Other than that, there is nothing in the question. So let's take the torque about the bottommost point. So if you take torque about the bottommost point, n ka torque is 0, friction ka torque is 0. You only have mg sine theta ka torque into small r is equal to minus ia about alpha dash. So this is mg sine theta r, and this is a solid sphere, so minus 7 by 5 mr square alpha dash. So we get alpha dash is equal to minus 5g by 7 sine theta by r. So we get the acceleration of the body is equal to r alpha dash, which is minus 5g by 7 sine theta. So how do you find alpha dash here? So look at this pair here. So if you look at this thing, so this is the A center of mass of this guy. So this is going with alpha. So here A of this guy is nothing but R minus R into alpha dash. Agreed? No, the acceleration of this, sorry, R minus R into alpha. Because the rotation of this line alpha, that is R minus R, will give you A comp. So we get alpha is equal to A by R minus R. This will be minus 5G by 7 R minus R sine theta. Now you will say theta is small. 5G by 7 R minus R theta. That will give you time period 2 pi root over 7 into R minus R by 5G. Check. So there are basically two alphas here. That's what you have to be careful. Or kuch nahi hai. Most common mistake is that only. We think like the alpha of the cylinder and you try to let with theta of the big one. All clear with this? Uh, it's like, there are people who's not keeping their cams on. I'll just kick them out. Just give me a minute. All clear with this? There, that's a bit about it. So that is based on Angular SHM. So we have done almost 45 questions on this. Now, what we have done so far, right? We are using forces and torques, but there is another way to solve these problems called energy method. So we'll do that also because there is a certain type of problems you can't use force and torque method. So better we have one more technique in hand. So what is this energy method? So the idea here is since the total energy of the system remains constant, we can use that to get the relation between A and X. Total energy of an SHM is constant. So what are the steps to solve here? Step 1, displace the system from the mean position. Right, by X. And let the velocity be V and the acceleration be A. Then you find the total energy of the system. And differentiate. Because the total energy is constant, one side you'll get a 0. Differentiate with respect to time. And then you will end up with A is equal to minus omega square X. You'll get this thing and compare with this. I don't like this method, except few cases where you are sure, okay, I can't solve this with energy method. You will need to know, right? We will see those cases. First of all, let's see why I don't like this thing. This thing actually becomes quite lengthy. Look at this example. So if we can do something with force method, you should not go here. Remember this one? So we have a block here, M here, and K here. Let's try to do energy method with this. So initially, this is your natural length. This was your mean. This was your Y. So initially, Y is mg by K. Great. Now, step 1, displace the system by X. So if you displace the system by X, Let the velocity be v. Now, what is the total energy of the system? The total energy of the system of k x plus y whole square. Be careful. Spring energy had to take the total potential energy minus mgx because you went down by x plus half mv square. So you have three energies here: spring energy, gravitational potential energy, and the kinetic energy. Differentiate with time. Left hand side will become 0. This will become 2 will cancel k x plus y dx by dt. Remember, y is constant. This will be minus mg dx by dt. Half mv square mv dv by dt. This is k x plus y. This becomes velocity minus mg velocity. This will become m velocity acceleration. But I already know ky is equal to mg. These two terms will cancel. Then v also will go off. Then you end up with ma is equal to minus kx. Then you get a is equal to minus ky mx. And then we will say this is your omega square. And then we get the time period from here. You get in the problem here? Lengthy, right? And what did we do with the net force method? Yaad hai? What did we see in the net force method? When you pull by x, what is the change in spring force? Kx. Did mg change? No. So therefore, kx is equal to minus ma. Done. So it was faster. So in the energy method, right, the headache is you need to find that initial values also. What is the initial elongation? What was that and everything? And you have to take care of everything. There is a good chance you might forget potential energy term. So it becomes complex, but this method has its own advantages. We'll see. But got the idea here? Let's do one more, but let's try to solve this problem with energy method. We have done a question like this. So let's take this as solid cylinder. We have a spring here. Let's take it 2K. We have one more spring here. This is K. Find the time period using energy method. Solid cylinder mass mr. No slipping. You guys give it a try. Let's use energy method and find the time period for this. You know how to do with the normal thing, but let's try with energy. Okay, let's see whether you got it. 2 pi 2k by m. Okay. Could be the answer. So what we do? Step 1, displace it by x. That is the standard story every time. Now, if you displace this by x, be careful, the top part will stretch by 2x. That you should know, right? And let the velocity be v and let the acceleration be a. And this thing will also rotate, omega and alpha. So there is a rotation also now. And since it is not slipping, a is equal to r alpha and v is equal to r omega. And this spring here also will move x. Perfect. Now, what is the total energy? Half k x square. This is that horizontal spring. Half 2k 2x whole square. That is the top spring. Half mv square, the kinetic energy, plus half I com omega square. That is the kinetic energy of the cylinder. So there are four terms. You can see where it is going. It's becoming lengthy, right? Steps are big. So if you differentiate this, we can simplify this further. How much is this guy? That would be 9 by 2 kx square. This would be half mv square. Solid cylinder is mr square by 2. So this will be 3 by 4 mv square. I com is mr square by 2. That is r omega is v. So that's 1 by 4. And this now differentiate. Once you do this, you get 0. This would be 9 kx velocity dx by dt plus 3 by 2 mv acceleration. Maybe you get a is equal to minus 3 will cancel. 3 will be left minus 6k by mx. Did I get it right? Makes sense. So yeah, that's your answer. Please check. Did anyone else get this? Yeah, Samya got the same thing. But getting the idea here? That's it. So this is your energy method. So you just have to get the energies and finish it off. It just goes lengthy. But yeah, there's nothing wrong. You can use whichever you like. I don't prefer this. But like I said, there are a few models where you will know, boss, the regular method won't work. So let's see what is one model there. And this is an important one. You should know this result. If you have a spring, capital M, this is small m and k, even if the spring has a mass, we have a spring with a mass, small m. Yeah, the mass of the block is much, much greater than small m. So for all purposes, it will act like a normal spring, but it has some mass. So here, right, there's one important assumption you should assume they will give. If they don't give, you still have to assume. Because the mass is very, very small, we can approximately assume this. Velocity of the spring varies linearly. What do you mean by that? Listen. Just look at the spring scenario here. So when the spring is attached, what is the velocity of this point which is attached to the wall? 0. What is the velocity of this point which is attached to the block? V. This is the velocity of the block. So that means every point on the spring has different speed. And he's saying this velocity varies linearly. So if you take this point as y and this position has a velocity v dash, then your v dash is v by L into y. So that's the linear function there. So every point will have different speed on the spring. So that information you should know. Find the time period for small oscillations. Here you can't do with the force method. That's because when the spring starts stretching there, the center mass gets messed up. We exactly don't know where to apply that force. So when you deal with springs with mass, you have to use this method, but we will get one standard result. You can directly use it next time. Give it a try. Using energy method. How do we do this thing? So just to give an idea here, what is the total energy? Half mv square for the block, half kx square for the spring, plus kinetic energy of the spring. Because every point on the spring is moving, you need to find the kinetic energy. You can find everything here except this guy. So if you can find this one, your job's done. So how do you find the kinetic energy of the spring? See, we have to integrate. So if you say this point is going with v, so at a distance y, take a small slice dy, whose velocity is v dash. The kinetic energy of the spring, you add up all the small energies, integral of dm v dash square. This would be half mass of the spring by length into dy. V dash will be v y by L ka whole square, 0 to L. This would be half mv square by L cube integral y square dy. This is mv square by 6. That is the catch. So the kinetic energy of the spring is half mv square by 6, right, Anvita? And then you are done. So total energy will be half capital mv square, half kx square plus small m v square by 6. Differentiate. The left-hand side will become 0. This will become mv, dv by dt is acceleration. This will become kx, dx by dt is velocity. This is m by 3 velocity acceleration. We get a is equal to minus kx by m plus small m by 3. It's a pretty good result to remember. So whenever you see springs with mass, you can simply replace the spring with an additional block of m by 3 and you'll get your answer. So you can remember this. Yeah, but it works only under that condition. Velocity is assumed to be linear. By chance, if they try to mess it up, then it will change. But generally, I don't think they'll do that. So masses are different, Rautsa. Capital M and small m, yeah, capital M is much greater than small m. They're not equal. So we take that mass is much greater because, or else if the masses are comparable, when the spring stretches, the spring density will change and everything goes for a toss. You can't assume dm is m by L dy anymore. Clear? That would create all issues there. All clear with the energy method. So this is a second way of solving oscillations. You can use it for angular SHM, linear SHM, anything. It works, but like I said, 99% of the problems your regular method will work. So there are few cases where energy method shines. This is one of them. Clear? The next thing is torsional pendulum. This is mostly theoretical, but there is a way to ask this as an advanced question by combining with elasticity. What is a torsional pendulum? Torso is what? If you look at your hip ka part, right, that's a torso. Now just look at your neck, okay? If you try to rotate your neck to the right, and if you keep on rotating more, at some point you can't rotate, isn't it? You'll try to come back. So your neck, right, when you're trying to twist, so this is actually a torsional torque. Where did you hear this word torsional torque? याद है elasticity में when we did this one, find the torque required to rotate the cylinder, torsional torque. You guys remember this? How much torque is required to rotate a cylinder? So it's basically the torsional thing. So when a wire or a rod is twisted, so best example is your neck only. Just sit straight and try to twist your neck to the right or the left. You will see like there is a stress on your neck, right? Eventually you will try to come back to the front. So when a wire is twisted, it generates a restoring torque. Twisting or a torsional torque. So for example, let's say we have a wire. We have a disc here. So here they will give you K, they will give you normally. K is the torsional constant. At a mains and bits level, they'll give you the value of K. Advanced they can ask, find value of K. So if this is O and this is A, now if you twist this by theta, so the wire gets twisted. This OA becomes something like this. So this generates a torque. So this torsional torque is proportional to minus theta. This is the angle twisted. So the more you twist, more torque you get. So this thing is looking like SHM, isn't it? So then we get torque is equal to minus K theta. K is your torsional constant that we wrote, and torque is equal to I alpha, that is minus K theta. So we get alpha is equal to minus K by I into theta. Therefore, the time period will be 2 pi root over I by K. So there are no questions on this. Matlab, pretty straightforward questions you'll get at a mains level. So for example, if you have a disk, K, so they will give you moment of inertia is mr square by 2. You should just know this thing. Substitute there, you get the answer. Suppose instead of a disk, if you have a rod, the moment of inertia is ml square by 12. Substitute there, you get the answer. Clear with this? If at all they want to play something, they want to really ask you something tough, they will do this thing based on elasticity. They'll bring this question into the picture. If you guys remember this question. So they'll give a question like this. They will say there is a cylinder, it is twisted by small theta, find the time period. So here the torque will be, if you guys remember the result, torsional torque. Tau is given by pi eta r power 4 by 2l theta. This is your torsional constant. Then they'll ask you find the time period of this. Then you have to derive this value. That's the reason it becomes an advanced question. Refer elasticity, page 59. Clear? But torsional constant, there are no questions as such. That's it. You give the value and you're done. Clear with this? So with that, technically, we're done with SHM. Now there's one part there called damped oscillation. Now this is removed from the mains portion. It's not there in mains, but it is there for advanced. It is there for bits, and it is not much. It is just a small theory there. But advancement, they can ask you questions based on AC circuits ka combination mein. But let's say it's a small theory. We will do that. So what are this damped oscillation? So let's say if your system is oscillating in presence of some kind of an air resistance or something, we will again study a very special case. So if the body oscillates in presence of a resistance, viscous force or some resistance, right? So it starts in a damped oscillation. So now this resistance force, we will study a very special case, which is equal to minus BV bar. So we are studying only for linear variation. If you see 6 pi R8 AV, yaad hai? Stokes law kind of looks like that. If it is BV square, BV cube, we will not do that. We don't have it even at an advanced level. It becomes mathematical. This also becomes highly mathematical. So we will just write some basic equations and we'll just see the final results. So this B is called damping constant. So B will tell you, so higher the B, the more the resistance. Think of like more viscosity. V bar is your velocity. So let's say we got a block here, mass m. Let's say someone displaced this by x and velocity v. The acceleration a. What are the forces on the system? We have a spring force, we have a resistance force bv opposite to velocity. Now when you write the forces on the system, we get kx plus bv is equal to minus ma. So let's write this in the next page. So this can be written as ma plus bv plus kx is equal to 0. So this can be written as m into d square x by dt square b into dx by dt. This is a differential equations which max people will teach you. Have a separate chapter for this. They'll teach you how to get a solution for this. The simplest differential equation is when b is 0. Remember, that was an SHM equation. That was the simplest differential equation which we have done so far. So how do we solve this? Like I said, again, we'll not go too deep into it. Just do how much is required. So this is b dx by dt. The end results are important, so don't worry too much about anything else. They're not going to ask you any derivation or anything. So this kind of equations, right, generally how they solve, they start with a general solution. I don't know how max people figure out there's a general solution here, but they do. So the general solution for this thing is x is equal to e power alpha t. So for these kind of equations, generally the solution will be in this form. So that will be a into alpha e power alpha t d square x by dt square will be a alpha square e power alpha t. When you substitute this here, we get ma alpha square e power alpha t plus b into a e power plus k into a into e power alpha t. So when you do this, you can clearly see you'll end up with m alpha square plus b alpha plus k is equal to 0. You get a quadratic. So alpha will be minus b plus or minus root over b square minus 4mk by 2m. So this can be written as minus b by 2m plus or minus root over b square by 4m square minus k by m. Yeah. So this is the alpha ka roots there. Now, if you see here, if this inside, right, the function, if the roots are not positive, it becomes imaginary. So at this point, we'll not bother about what is happening here. Then there are some mathematical solutions for this. So we have different possibilities. So just remember these things. These are important. So case 1, if the roots are positive, that means inside if b square minus 4m square is greater than this. So if b square is greater than 4mk, the roots are real. That means, and you remember your solution, x is equal to a into e power alpha t. If you actually observe here, we got alpha ka 2 values. So what people do, right, they actually write e power alpha 1t plus e power minus alpha 2t. So they take both the roots, alpha 1, alpha 2, and then they write it down. That is the general solution. So alpha 1, alpha 2 are the two roots. Again, all this is not required at a mains level, bits level, even advanced level. What matters is the end result. So these roots are real. So this is a case of overdamping. We'll discuss about that. What is that? So this is called overdamping. Means what? Look at the solution. We got x is equal to e power alpha t, right? And if you see here, if you take that alpha ka value, which is negative, meaning the system is not going to oscillate. It is just going to decay. Matlab, you start from one position, it will just tend to 0. I'll show you the graph. So basically there'll be no oscillations. So if you have a system which is overdamped, if you try to disturb it, it won't oscillate. That means when you stretch it and release, it comes back to the mean and stops. That's it. There'll be no oscillation. Best example, right? Did you ever see this thing? Some office ka doors have a spring ka system. Kabhi observe kiya? You have a door there. On top of this, you have some kind of a box here, and it is connected to a rod like this. Ever seen that? When you open the door and leave it, the door just aram se closes and just stops. It doesn't oscillate. Do you guys understanding what I'm talking about? It's a door with a spring on the top. Never seen that? I should have got a picture for that. I'll show you something else. But so if you have a spring door, right, in an office or something, and you open it and leave it, it just comes back slowly. It doesn't just bang the door or something. It just comes down aram se and stops. You guys have never seen anything like that? Especially when the glass doors are there for an office, right? They install it. You don't want that glass door hitting it and the glass cracking. Another example, right? When you're going on a vehicle, your bike or something, the shock absorbers are there, they're overdamped. Think about it. Every time you fall into the ditch, you want the springs to come out aram se, or you want the springs to just kick you from the down? You want it to go aram se, right? Imagine if they're not overdamped. You know what will happen? Every time you fall into the ditch, you'll be oscillating like a spring up and down for some time. You'll have a very bad ride. Right? The shock absorbers are overdamped. So whenever you're designing a robot or any machines, right? Generally we use overdamping. Imagine you design a robot and you don't, overdamp the hands, and you tell the robot, give me a pen. It will take the hand, it will give it to you, and the hand will just keep vibrating and keep punching you. So you want the hand to come and stop at you, right? You don't want the hand to oscillate. So if you have b square is equal to 4mk, the roots are equal. So this is called critically damped. This behaves exactly like overdamped. The only difference, so here also there will be no oscillation. The difference is this. It will come back to the mean position in the least time. So this is also overdamped ka case, but this will happen in the least amount of time. It comes back to mean in least time. So if I try to plot the graphs for these two guys, this is how it looks. So this is your displacement from mean position versus time. So let's say if this was your amplitude, so you displace the body by A and you release it with damped oscillation. This is the overdamping case. The system will aram se come back to the mean. Yeah, it will take time. The other case, this is critically damped. You will also come back to the mean, but you will go the fastest. Now, how it depends? It depends on beta value. If you have more this thing, you will reach the mean position faster. So this much you should remember, okay? They'll ask you, find the condition for overdamping, find the condition for critically damped. That much theoretically they can ask you there. Clear with this? And how did we get this? Think about this. If the general solution is e power alpha t, and if alpha is a negative number, so e power minus alpha t, how will the graph look like? Won't the e power minus graph look like this? It is just a decay function. It just drops and stops. Clear with this? Now there is a third case. What if the roots are imaginary? And they can ask more questions on Generally, mains and bits में they used to ask questions on this case. If p square is less than 4mk, the roots are imaginary. This is called underdamping. So what happens in this case? So m square dx square by dt square. Chalo, focus everyone, don't get distracted. Kx is equal to 0. For this, the solution is x is equal to a e power minus bt by 2m sine omega dash t plus phi. So this will be an exponential thing with a sine function beside. The amplitude will be a into e power minus bt by 2m. So this is a sine function whose amplitude is decreasing. So omega dash is root over k by m minus b square by 4m. And the time period will be 2 pi by omega dash. So these are all the things they can ask you. In an underdamped oscillation, find the amplitude, find the omega dash, find the time period. And how will the graph look like this? This is a sine function whose amplitude is decreasing. The graph would look like this. You're getting? It's a sine function which is continuously the amplitude is dropping. This is a decreasing amplitude. Clear with this? So how does this look? Look at this. So what they're doing, right? He got a scale, wooden scale, and he kept a magnet. So this thing which you can see here is a magnet. And at the back, there is a metal ka sheet. So the magnet is getting attracted to the metal sheet. Okay? Now see what happens. If you bring that metal sheet closer, the magnet will attract the metal sheet more strongly. So it will get more drag, isn't it? So instead of viscosity, here we are using magnetic attraction as a drag force. So the closer the steel plate, the more the drag. So the farther the steel plate, lesser the drag. So now the plate is pretty far. So there he kept the plate there, and now he is going to push it. Now see, he's leaving it from here. I think there's a little lag. I'll post it anyway in the group, but have a look at this. Now when he leaves it from here, see how this thing will move. It goes left, right, left, right, left, right. This is underdamped. See, it is continuously oscillating. It doesn't just stop. This is a case of underdamping. Because you kept the metal plate very far, the drag is very small. So this will oscillate, 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 and eventually stop. This is the case of underdamping. Now he brought it more closer, see. Now attraction will be more stronger. Now see what happens. This is also a case of an underdamping, but it stopped faster. So that is 10 mm ka distance, okay? Now he's bringing it even more close. 8 mm. So 8 mm is the distance between the metal plate and the magnet behind. This is also underdamping. It is still oscillating. See, if you cross the line, the green line means it is underdamping. He brought it even more close. 6 mm. This is still underdamping, but it stopped very fast. Did you see? It just did 1-2 oscillations and stopped. You guys are able to see that? There was too much of a lag. Then let's see more. 4 mm, it's too close. It just did 1 oscillation and stopped. He brings it even more close, 2.5 mm. This is almost critically damped. Did you see what happened? It just stopped. He's almost touching it now, 2 mm. There, it just stopped. See, it didn't even cross the green line. It just came there and stopped. This is almost critical overdamped. 1.5 mm. It just stops. It just comes there and stops. It doesn't cross the green line. If you almost touch it, 0.5 mm, it just stops. There, you can clearly see this thing. This is like super overdamped, like just a drag and stops. Is that clear, everyone? You're getting what I was saying? Damped, overdamped. So that was what was happening there. I'll post that in the group. So do check it out. I think there might be a little lag. So, but that's what I was saying. So in case of over damped, you will go slow and stop. In critically damped also you'll stop, but you will take the least amount of time. Under damped, you will oscillate left, right, left, right, left, right, but you'll slow down. Clear with this? So in this, the kind of questions I can ask, right? There's generally only one model. Let's do that. Easy one. So the amplitude of a damped oscillation, at least at a mains and bits level, they won't exceed this. Given by A is equal to A naught e power minus bt by 2m. Find the time when the amplitude and the energy becomes half. That's it. This is the kind of question they can ask you based on the underdamped case. And it is there for CET. Yeah? This is there in HS. Let's get this. This is direct formula substitution. In chemical kinetics, if you have studied, do you guys remember? Doesn't this look like N is equal to N naught e power minus lambda t? Chemical kinetics, first order reaction. It looks like that. Mathematically, they're the same thing. There you call lambda as the decay constant. Here we call B by 2m as the damping constant. Finish off. Last one for the day. And with that, we are done with the chapter also. First one, you want amplitude half. So A naught by 2 is equal to A naught e power minus bt by 2m. Put ln on both sides. We get ln half minus bt by m. So we get time is equal to m by b ln 2. Yeah. What about energy? Energy is half m omega square a square. So energy is proportional to a square. That means for half energy, amplitude should be a by root 2.
So 2m the other question.
Yeah.
It's 2m in the question, right?
2 hai. Yeah. A naught by root 2. This will be A naught e power minus bt by 2m. Same story. Put ln on both sides. I think यहाँ पे 2 नहीं आएगा. M by 2 ln 2. Easy. Yeah, ln root 2. Then you can bring an half outside, na? That goes off. But this was the question whenever they asked on damped oscillation. This was the question they used to ask in mains and bits and CET. They never go beyond this at that level. So there, we have done almost 47 questions on SHM, right? It's a very good chapter. SHM is still not over. Matlab, every time I teach you a new chapter like electrostatics or gravitation or magnetism, SHM will keep coming. It will always keep coming as a part of some other chapter now. So it's a never-ending thing. So please start solving SHM. Next class when we meet, we are going to start off with electrostatics. So we are starting a very important chunk now, right?